share that screen.
I need to share that screen actually,
Yeah.
right?
Yeah.
So let me. Then I have to display this, and then I needed to escape this to go to Zoom. Zoom, share, screen 2, right?
Yeah, screen 2.
Okay, I think we're good, Alice. Okay, can you see now? Okay. So thanks everyone. Sorry for the technical challenges. As I mentioned at the beginning, we had some slight technical challenge with this. We are still part of the iConnect Youth, and our speakers are lined up, and our panel is going to be Liso and Alice and myself. And for our speaker right now is Professor Jacob Jones. Jacob is the director of STEPS, which is a very huge center, big project, big ideas. He is a hardcore material characterization ceramics person. He does the kind of stuff that I used to see in class and run away with hard x-rays and all that. But he has actually taken a very interesting time and started looking at phosphorus sustainability. And he's a perfect fit to what we're trying to do right now. And with that, I would like to ask Jacob to take the reins, and then we'll take it from there.
Thank you. It's my talk now?
Oh, sorry. Let me share your slides. Yeah. Okay. Yeah. Okay.
Thank you for
Yep.
your patience.
Yep. Yep. All right. Okay. Thank you. We are here. We'll be okay. Okay. All right. Go.
Okay. Thank you, Martin Thuo, for that introduction. It's an honor to be here to represent a couple of different projects. As Martin mentioned, the STEP Center, which is a center focused on phosphorus sustainability, a new area for a material scientist to grow into, and I'm excited to share that with you. Okay. Thank you. All right. So, sorry for the technical difficulty, and I'm glad that we're now getting going. An important aspect of the STEP Center is that, and I think this is consistent with the philosophy of this meeting, we're not just interested in tackling a specific problem, but we're interested in tackling that problem with a very carefully defined perspective, and also using a very intentional process. And so when you work on complicated problems in this space, it's important to have highly interdisciplinary contributions, and so STEPS is one example of doing that for phosphorus sustainability. But before we get started talking about phosphorus sustainability, I thought in the spirit of this meeting, it would be useful, maybe instructive, to answer these questions, science for what and science how. And this may be a bit of a cynical view of the material science discipline and maybe nanotechnology as well, but we can't just be developing structured property processing relationships. We have to be developing it for something, and something of societal relevance. Now, many of you in this community already know that. You're already motivated by that. But we need to go back into our scientific disciplines and continue to advocate that we're doing something of relevance to society and we're doing it in the right way. And then in part 2, I'll introduce the challenges underpinning phosphorus sustainability, which touches upon the African continent, but we're going to have a global perspective to it. And in part 3, if I have time, highlight a few exemplary research highlights from the STEP Center, starting with a global perspective and then narrowing it down to some local things. Now, many of you in this scientific community understand nanotechnology. There are different initiatives across the globe. In the US, it's the National Nanotechnology Initiative. But we go out to high schools and we say nanotechnology is important. And usually we show this link scale diagram that shows that nanotechnology spans 9 orders of magnitude, all the way down to very little things that do very important functions. And my argument again is this is great, but nanotechnology for what? What problems are we solving? And many of you in this community know that you can pick from the UN Sustainable Development Goals to find specific challenges of relevance to your scientific interests, and then use that for your motivation. And I say back in the US, from our perspective, we also have the National Science Foundation's 10 Big Ideas. We have the National Academy Grand Challenges. But again, it's critical to justify ourselves, our value proposition of our discipline, to tell society specifically what we're improving in the human and earth condition. And when I look at these SDGs, I see really two categories of things. One is the human experience, human health, and then the second is earth. And one of the problems that we've tackled in the STEP Center is related to that second challenge primarily. And I think this is a great diagram that illustrates some of the compelling challenges around what we now define as climate change. I think I can say that outside of my country. I'm not sure I can say that inside my country now. This wonderful polar plot represents something Jackson was mentioning earlier about how far out of our planetary boundaries we exist in these respective areas. So in the polar plot, we see particular areas that are in red and some areas that are in green. And if it's in green, we're in a safe operating space for humanity. If we're in yellow, orange, red, we're not in a great space for humanity. Right? There are key challenges that we need to address. And history has told us that we can do it, but we have to act, and we have to act quickly. In our particular case, we're interested in phosphorus sustainability, which is in the lower left-hand corner in the biogeochemical flows quadrant. But again, big, challenging societal problems. And so what is the scientific approach that should be used to solve such problems? And we adopt in our center the philosophy of convergence research. This was catalyzed back in the US in 2011. Many of you may think that this is transdisciplinary work, but it's actually transdisciplinary work applied to a very specific, compelling societal problem. So it has a very relevant, specific definition. And it was said, and I love this quote because it references Thomas Kuhn, so it points to science philosophy in some degree. It says, the convergence revolution is a paradigm shift, but not just in Thomas Kuhn's terms, a paradigm shift within a discipline. It means a broad rethinking of how we conduct scientific research. Not only are we doing it across disciplines, are we engaging stakeholders out there in the community that are actually going to be adopting these approaches and these tools, best practices, and technologies. And then from our perspective, it was very important that the U.S. National Science Foundation adopted as one of its 10 big ideas growing convergence research. This was in 2018, right before we proposed our center. And they recognized the importance of this approach for things related to human health and the food, energy, water nexus. And then we proposed and won the STEP Center. So the STEP Center is the largest research center, or research project in the world that's dedicated to studying phosphorus sustainability. It was funded in 2021. It's a National Science Foundation Center, so it's necessarily US-centric in its participation. But again, we have this global perspective in the problems that we're solving. Many of the institutions are shown there. And importantly, we've been described as a convergence research center, going back to the process, with phosphorus sustainability as the vehicle. That's the target of our work. So two very important things about what we do. So why study phosphorus sustainability? Just by a show of hands, when you walked in here today, did you know that phosphorus is essential to your food security? How many of you? Okay, I see about 50% of the people in the room raising their hands. Okay? So we'll unpack this a little bit. Phosphorus is an essential nutrient for animals, plants, and microbes. It facilitates cell development. It's an important component of molecules that store energy, DNA. Even the recommended daily allowance, depending on your part of the world, could be anywhere between 500 milligrams to 1,000 or 1,250 milligrams. We store it in our bodies, mostly in our bones and teeth, and so it's very important as a child that you have this in order to grow. And importantly, phosphorus drives crop yields in the food system because of its influence on plant growth. And if you want to see that directly, you can pick out your favorite crop or your favorite food, and you can download yield data for your particular area of the country or from wherever you source that food. And you can trace back to about 1930, 1940 in agriculturally producing countries of the world or areas of the world. You can see that the increased application of so-called mineral phosphate fertilizers has resulted in consistent increases in yield. This isn't not just the application of mineral phosphates, but the green revolution and a whole bunch of other complementary things. So this is important in appreciating its value to the food system. But the origin of phosphate fertilizers is in phosphate rock primarily, and that's distributed disproportionately throughout the world. And so I've drawn from US Geological Survey data, but this is pretty consistent across different data sources. You can see the reserves in different countries shown in blue in the bar at the right, and you can see the mine production, the annual mine production in the gold bar. And so we can immediately see a few outliers here, right? Morocco holds 70% of the world's phosphate rock reserves. And that is one of many reasons why it's important to have these conversations in Africa. I'll bring up another reason later. And then China is the world's leading producer of phosphate rock, but they limit the amount of exports that go out, and so this affects the economic aspects of phosphate fertilizers. If you look at something like the price of phosphate fertilizers over the past many years, you can see significant price fluctuations. The first one, which occurred around 2008, which was almost a tenfold increase. Could you imagine being a small farmer and having one of your supplies increase by 10x? So this had devastating effects to certain small farms. It seemed to stabilize over a period of years, and then recently has been going up, and then more recently even fluctuating a little bit. But it's driven by things like war and pandemic and tariffs, okay, which we're all becoming too familiar with these days. So I know you all you're all scientists, and so you like quantitative data. So I want to throw a few numbers out there for you. This is the historical global sources of phosphate fertilizers from 1800 to 2000. You can see this green at the bottom. This is manure. It's still used as phosphate fertilizers, but on top of that you see the red, and the red is phosphate rock. Again, you can see around 1930s, 1940s, this inflection in the amount of mineral phosphate fertilizer that we're extracting from the earth and applying to our fields to grow crops. And I've identified a couple other relevant things here, but the takeaway here is that since 1950, society as a whole, globally, we've increased our global phosphate mining dependence tenfold, from about 2 million metric tons per year to over 20 million metric tons per year, and it continues to grow. Now, material scientists in the room may say, that's a really interesting number, 2 million metric, 20 million metric tons. What does that actually mean? Okay? And to bring this to something you're more familiar with, and bauxite was also referenced earlier today. We globally mine 380 million metric tons of bauxite per year, from which we derive 140 million metric tons of aluminum. By comparison, phosphate rock is 220 million metric tons, from which we yield about 20 million metric tons of elemental phosphorus. And you can compare it to any of your favorite elements. Of course, phosphorus is my favorite element, but compared to your favorite elements, in lithium, you're looking at orders of magnitude different from that, right? Now, the interesting thing about this, and you'll see this on the next slide, is that while we're pretty efficient with aluminum, how often do you throw away 50% of your aluminum? You don't often do that, right? While we're pretty efficient with aluminum, we're very inefficient with phosphorus. So in the food system, 80% of the phosphorus that comes into the food system is lost. Humans only eat 20% of the phosphorus that comes into the food system. Imagine if you do that with your shampoo. I mean, who in their right mind would throw away 80%, right? So it's something that we're going to have to grapple with as society. And as scientists, we often want to understand this from a mass flow perspective. Oh, do these numbers make sense? And this has been tracked and vetted many times. This is an exemplary phosphate flow diagram starting with phosphate rock. And the numbers here are 1 million metric tons of phosphorus per year. The arrows represent the relative sizes. So you see big arrows is a big annual mass flow, small arrows is a small mass flow. And you can immediately notice a few things about this. If you look at the agricultural sector and you put a circle around it, do a mass balance, you can see that a lot goes in and very little comes out. And this points to the fact that we're building up legacy phosphate in agriculturally productive areas of the world. And you can also see losses of phosphorus to surface waters, which causes eutrophication and harmful algal blooms, and then eventually methane emissions. So it's connected to the carbon cycle as well. And finally, I'm just going to point out humans. Small little box here. 3.5 million metric tons comes in. That's the 20%. But importantly, it's our decisions that affect this entire system. And it's not just your individual dietary decisions that you make with your doctor. It's also the decisions we make as governments and public policy and things like that. So it's our opportunity to influence this in a different way. Now there are significant downstream impacts and consequences. You could talk about this in the context of environmentalism. You could also talk about it in the context of economics. It simply does not make sense to ruin our environment this way because of the negative consequences it has to so many other aspects of life. Just to put one piece of data on it, and again, we're a U.S. center, but I hope you appreciate this from a global perspective. Our U.S. Environmental Protection Agency has documented that 50% of our lakes are in poor condition with elevated phosphate levels. Now, as other areas of the world grow in agricultural productivity, we hope that they don't make the same mistakes that we did. Okay? And that you're in a better position. One ultimate consequence of this on our side of the world is the phosphorus that flows from the Mississippi River into the Gulf of something.
Mexico?
The Gulf region, right? And this causes one of the world's largest hypoxic dead zones where no fishing can happen. So again, economic consequences of that. All right, so what will the future bring? Jackson mentioned that some statistics related to the number of workers in Africa. I bring to you United Nations data that shows the expected explosion of the population in sub-Saharan Africa. This is, you know, the purple one that's going up very rapidly with a very strong slope. So if what we're doing today in agriculturally productive areas of the world doesn't change when other areas grow, they're going to experience similar problems to what we've had in the past. And this is why it's important to think about a step function in terms of what we do in these emerging areas of the world and their evolving agricultural efforts. And I wanted to make this a little bit more specific, and so I scoured some scientific data, and I found down at the country level some specific projections for the amount of phosphate fertilizers that are going to be required as we move forward with that explosion boom, with that population explosion boom. And you can see here the top one would be Nigeria. From 2020 to 2050, just 30 years. Over the young life of a teenager blossoming into an adult, you can see that we're going to require an additional 934% in Nigeria. So a challenge in phosphate fertilization is getting it there and then using it sustainably, okay, in order to meet those demands for agriculture. And so you can see that the challenges underpinning phosphorus sustainability are challenging. Some people call them complex. And one of the ways that we like to represent that complexity in our center, and looking back to the nanotechnology diagram, we appreciate that the challenges underpinning phosphorus sustainability span 17 orders of magnitude in length scale. Not only are we dealing with the individual phosphorus atom and the phosphate molecule, PO4, all the way up to the scales at which humans interact with technology, think about farms and wastewater treatment plants, but also up to regional and global scales when we think about watersheds and we think about global economics and public policy affecting some of these flows. And so with the limited time that I must have left, I wanted to show a few research highlights. And I wanted to start at a really big scale and then drill down to some local scale to make it rational. And so the first highlight is a paper that the STEPS team published maybe a year or two ago, inspired by the observation that wars and pandemics influence phosphorus availability and phosphorus prices. And so the team unpacked from a systems level perspective some of the factors and interdependencies in these areas, and was not able to show how they influence the phosphorus markets, but was also able to suggest some interventions and some areas for scientific pursuit for groups like this. And one of those would be in improving phosphorus use efficiency in plants. The better we are at being use efficient in plants, the less susceptible we are to those global markets. And the second is utilizing legacy soil phosphorus. So if there are any soil scientists in the room, you know this has been a long studied problem, but it's a problem of high importance, in particular in areas where there is a lot of phosphorus already in the soils that can be released. And then the third is in leveraging internal phosphorus recycling loops in manure and wastewater. Our waste, whether it be animal manure, human waste, wastewater, contains a lot of phosphorus, and if we're not actively developing technologies to recover it, it's lost. And the second example comes in a paper that was just published last year led by Jim Elser, who's literally written a book on phosphorus sustainability. So you can unpack this later by reading his book. I didn't bring copies with me, but we'll bring him to the next meeting for signatures. And here in this paper, we take the quantitative phosphorus flow diagram, and you can see this as a graphics rendering at the right. And we say, okay, if it flows linearly from phosphate rock into wastewater and landfills, what can we do to increase circularity? Where is all the mass of phosphorus, and what technologies or practices do we need to develop to recover it? And so the STEPS team here categorized a couple of different things. One, ecological prospecting, thinking about how do we take large, complex data sets, remote sensing, and AI, and say, where are all the hot spots of phosphorus in certain geographical areas? You know, in Africa, it may be in a certain area. In the US, it may be in Europe, it may be in a certain area. But the idea is that we don't totally need to be dependent upon mined phosphates. We need to know where we can source it locally. And the second is ecological mining and ecological refining, converting various forms of phosphorus-containing materials to physical or chemical forms that can be put into practical use. This is an area that I know some of you in the room are working on. Jan Genzer is a chemical engineer here, and this is something that he does. We look at chemical transformations of phosphates. It's also critical to releasing phosphorus in legacy phosphorus soils. We have a team that's been working on mapping phosphorus flows across continental scales, and no matter what continent you're from, I hope that you can map this idea onto your continent, thinking about combining diverse data sets to get a complete map of where phosphorus is in hydrology or in soil science. And so here we can track annually the amount of phosphorus inputs and the amount of phosphorus losses to water resources. And that's very powerful in thinking about where we want to implement new technologies. We want to implement new technologies where they can make the most impact and the most sense. And the second to last example is in wastewater. And in some wastewater treatment plants, there's a process called enhanced biological phosphorus removal, or EBPR. And in certain parts of the world, this is a tertiary, so it's a final process that's required to get the levels of phosphorus down in the effluent to a point where it's below regulation limit. So it's not everywhere in the world, but it's in many parts of the world. And this EBPR process, for the most part, is pretty stable. The graph that you're seeing there, I don't know how big you can see this on your screens or in the room, but the graph shows, as a function of time on the x-axis, the amount of phosphorus that's coming out of the wastewater treatment plant on the y-axis. And you can see it's low, which means it's working well. There's little phosphorus coming out of the wastewater treatment plant. And then all of a sudden you see these spikes. And so the wastewater treatment operators and the scientists, no one knows why these spikes happen. A quote there is from the wastewater treatment operator that essentially says these bugs, he's calling them these bugs, you think they're going to work, and for the reasons that are completely mysterious, they decide one day to stop working. So it's an unreliable process. And so we can bring science to bear. And so STEPS has developed new microbe sample prep and microscopy methods to preserve and characterize the poly-P structure and the composition. You can see some examples of some of that imaging at the lower right. So this is, in our opinion, some of the best high magnification imaging of these particular phosphorus accumulating organisms in the world. And what we're able to learn is how metal cations co-locate with the phosphorus in certain granules and allow us to quantify that. And now that we have that ability to quantify it, we're doing something in a new project which is pretty neat, and that's what's listed at the bottom, which is developing next generation EBPR technologies using drop-in gene editing microorganisms. So we're working with geneticists on this. So that's a pretty exciting project. And then finally, in the last example, I want to highlight that STEPS has a lot of work in the area of sorbents for phosphorus recovery. And so sorbents are this general word that we use for solid materials that enter these aqueous matrices and capture phosphorus. Sometimes we can capture it and release it for other use, or sometimes it's permanently captured. And the team's looking at a lot of different examples: metal organic frameworks, hydrogels, nanomaterials, and polymers. There are some commercial materials available. The photograph in the upper left shows the application of PhosLock, which is a patented technology based on a doped bentonite mineral. And the application of this is either just in powder form out in the environment or in slurry form, but it's never recovered. I was so surprised when I learned this for the first time. We have absorbent material that sometimes contains rare earths, and we put it out in the environment and it's never recovered. And so not only is STEPS developing a fundamental knowledge of the mechanisms of absorption so we can have the best performing materials, but we're also thinking about how do we deploy it on a scaffold that can be recovered so we can reuse that phosphorus as a fertilizer. Now I'm getting a nod from someone in the room who just patented a hydrogel that does precisely that, so maybe he'll share that work with you later at this meeting. But just for a little bit of inspiration on the right, and I scrubbed the legend on purpose because we haven't published the data yet, so I don't want you to know which one's the best performer. But the data at the right shows, depending on what your initial phosphorus concentration is on the x-axis. So in some lakes it's going to be very low, in some wastewater treatment plants it's going to be a little bit higher. Depending on your initial peak concentration, you can see on the y-axis the amount of phosphorus that's captured. And you can see large variability here. And I will tell you, and you have to keep this a secret because no one's listening, I will tell you that the commercial materials do not perform the best. Some of these other materials are better performing. So there's a lot of opportunity in this space to develop more efficient phosphorus sorbents that can recover phosphorus for reuse. And finally, I think I just got the 3-minute warning, and I would say that I told you I wanted to present you 3 things, and I presented you those 3 things. But there's one more thing. And I want to come back to the convergence aspect of this. When I started down this road as a material scientist, trying to understand what's going on in this very messy space, one of my colleagues, who's a soil scientist, Dean Hesterberg, showed me this diagram, and I've redrawn it for you, because his was in black and white. And where I started was on the far right. I was studying very ordered, very highly crystalline, highly pure materials. And I jumped into a field where things are disordered and complex. The matrix complexity and the uncertainty is just tremendous relative to the type of stuff we were looking at before. And what we articulated in an MRS bulletin about this is where the opportunity space is. And thinking about all these sophisticated techniques that may be applied to the right-hand side, applying to the left-hand side. And the types of techniques that are applied on the left-hand side, maybe squeezing them a little bit to the right as well. This is one way to think about convergence is in this context, in this spectrum. And then finally, one final thought. When people start working in areas like this, sometimes they resist. And I think we all know someone in our discipline or in our organization who wants to work by themselves or work in a disciplinary silo, and they're resistant to convergence. And I think this happens a lot at the outset of convergence research projects, is we see this confrontation. But those of us that are believers that we need to have an interdisciplinary approach and we need to broadly engage stakeholders in the process, we need to be advocating for this collaboration. And we hope that this comes after this confrontation phase ends. And in the words of Mike Rocco, who is really just a shining beacon of intellect in the National Science Foundation, through convergence, people interact and understand better, and converging technologies offer means of reaching common goals by collaboration. And I think I'll just end with that. Thank you.
Great. Thank you, Jacob. Yeah, so we're not switching laptops. Things are changing rapidly here. Martin got pulled away. So I will introduce the next speaker, Benjamin Kwasa. Yes. See, my Swahili is getting better and better. Benjamin is coming to us from Kent State, but of course now I probably can't even find it. It was moved. A second. It's in itself. Do you remember what it was? Oh. Don't want to see that.
No, we don't want to see that. It should be Messiah Simona Jet.
No. Third one down. Okay, 1 second. Get through the Zoom. Nope. No. All sorts of things going on here. course, now Martin's calling me, so this is gonna be wonderful. Give me 1 second. Hello, Martin.
Hello?
Nope. You're talking to. Oh, there we go. Yeah. Getting there. Oh, share screen 2. That one. It's a lot of coordination. I'm going to put this. 1 second. Perfect. All right. Nope.
Which of these?
Okay. So, without further ado, Benjamin Kwasa is going to talk to us a little bit about design, value-driven design.
Yes. Thank you very much. Martin likes to put me in uncomfortable situations. I think he enjoys very much doing that. So you'll find that my background is a little different, and I'll start off by sharing my background and how I find myself in this place. I am a fish out of water, as they say, but hopefully there's some connectivity that can be made with regard to the thought behind innovation, manufacturing, and particularly its application to Africa. So I first describe myself as a father of 2 and a husband, and then I walk out to do my part-time job, which is the academic and research stuff. And at the end of the day, I leave that and then go back to my full-time job, which is my 2 kids who are my bosses in life, right? And I always bring that up because after I had kids, my perspective on the entire world changed, okay? And I'll tell a little story as to why, and hopefully this makes sense. When I was in high school, my father enjoyed presenting me with puzzles that he thought would be challenging to solve in his fun way of bonding. So his approach to he and I bonding was to test me intellectually and keep doing it until he got a satisfactory response. And so one such day, he asks the question while we're at the dining table, what does it mean to be successful? Okay. And I thought about this for a few days, and every day he came back and asked, so have you found an answer? And I said, not one that I'm happy with, right? Because for everything I thought was in one moment a brilliant definition of success, I could find ways to poke holes through it. And then I would quickly disappoint myself and go back to the drawing board and say, I'm going to try this activity again, okay? And each evening he comes back and he asks, have you now found what your definition for success is? And I would try again, come back, no response. And I hate giving up. And so one day, we're having dinner and he says, do you have a definition of success? I say, I have exhausted all possible definitions I can give. I don't have an answer, but I'm not going to give up. So I might spend the rest of my life trying to figure this out. And he said, would you like some help? And he knew that that would irk me, seriously. But I said this one time, yes. Yes, please help me in defining success. And he broke a rule that I had been taught throughout my time in school, which is you do not use words to define those words. And yet he said, success is when your successor succeeds. And I was puzzled and frustrated, and I told him, please explain. And he said that he was once told, the only time we as people can count ourselves successful is when those people of whom we are responsible for will walk this earth and they will count themselves successful. And once I had my son, I thought about this often. And then my second child came along and I thought about it a whole lot more and asked myself, why do I do what I do? Okay? And when we're in an avenue where we have such a diverse group, which means we have diverse thought, the question becomes, what is it that we do that will ensure that at the very least those who come after us are going to be successful in what they attempt to do, right? And so I think it has a little tie into what we like to define as sustainability, right? And I'll touch on that in a second. So I'm going to share a little more about why I say I'm a fish out of water. My background is aerospace engineering, and I do complex system design to put food on the table and so that I stay intellectually stimulated. And so with that is looking at systems, right? One of the first things we learn about anything that's considered an aerospace system is that it's very complex in nature. And so you go down this path of understanding or trying to define what a system is, okay? And so that's always the starting point when I'm engaging in any project. It's always the starting point when I'm teaching my students in class. Always when I'm trying to figure out, well, how does it fit in, okay? And so we simply define a system as a collection of entities that produce a unique behavior, right? Aerospace systems, aircrafts, fighter crafts, drones, we characterize and define in much of the same way. That is the last time I'm going to put a mathematical equation there. But it's what we use in order to define, test, and then quantify relationships that exist that allow us to confirm that indeed what we're looking at is a system and one worthy of the attention that we typically use when we are addressing a system. The second thing is value. Okay, what is value? Value I define as being able to elicit or extract usefulness from an outcome that we're interested in, right? And so we begin to put together building blocks of what we hope at some point is going to lead us to sustainability, right? And so we can have systems that exist outside of having or extracting value from these systems that exist, right? And I think the ideal state is when we can combine these two things, where we can identify systems, we can create systems, or we can have the intent to create systems from which the result should be we can identify and use some aspect of value from its behavior once it's created. I have only very recently started exploring the idea of sustainability because Dr. Thuo loves to pull me out of my comfort zone. And we've had lots of discussions as we do when we get together. And he works in materials and chemistry and I in aerospace engineering. And on the onset, there might seem not too much in common with regard to what we do. But as we continued having discussions, we discovered that a lot of what we do has characteristics that are similar, even though the domains in which they exist are often never interacting, right? I think this is the first time I've been in a room with so many people that have intimate background in manufacturing and in materials and chemistry. That almost never happens in my life, okay? In most meetings I'm in, we're going to be talking about aerodynamics, we're going to be talking about structures, and we want things to be the most powerful they can be and go as fast as they can be, and often ignore the rest of the environment, right? But when we look at what characteristics we have in that environment, I've been finding there's a lot of similarity with regards to what happens when we provide systems their context, right? Something that I have observed in other areas of life, be that government, be that justice, be that political action, or even social interaction, is we are resistant to change. We are very resistant to change. And in the work that I do, something that we acknowledge is change is absolutely necessary in order to maintain desired outcomes, right? We typically design aircraft over a period of 10 to 15 years, right? And then upon the design of aircraft over a period of 10 to 15 years, they stay in service for decades, right? The longest production aircraft known to mankind is a small aircraft known as a Cessna 150. Okay? Some people might be familiar with it. If anyone has ventured down the path of trying to get a pilot's license of any kind, that's often the first aircraft you put in, right? Cessna 150 is a small two-seater aircraft with a piston prop engine. Most of the human population will never interact with it, nor will they know what it looks like. But it is the longest running production aircraft known to mankind. Started in the 60s, and we produce them till this day. The only way that is possible is to make sure that in as much as it stays the same, it has to constantly change. Keeping a Cessna 150 in the exact form that it was designed in the 60s would make it obsolete in this day and age. So a vital part of aerospace design is ensuring that part of the design process is accounting for the fact that if we're going to continue engaging in a certain activity, we must make sure we constantly innovate and change it to match up with the context. And that context is the environment in which it exists. Right? And so if we look at our environment, be that in Africa, in America, in South America, in Asia, in Europe, in Australia, even at the two poles, right? There is a lot that stays the same, but there is even more so that is changing. And so your ability to maintain usefulness of anything you have in this environment has to go with the confrontation of change that comes in one, the other, or both. And so when we think of sustainability, I think of it in terms of three key characteristics. The time scale, right? As a systems engineer and as an aerospace engineer, I'm interested in time scales because something can be deemed effective if it only needs to work once, right? When we study ballistics and missiles and rockets, we only needed to work right one time, right? And that's considered very successful. If my Cessna only flew the one time, that would be considered highly ineffective. Yet these two things share a lot of fundamental differences to them, right? In fact, the groups of people that create one are often people that have trained with those that create another, right? And so we find within the realm of aerospace engineering that the time scale is very important into defining, can I maintain this activity, right? And I think it applies in this case where, as has been mentioned, we are looking at environments that are in different points in time from a technological advancement perspective, from a demand of resources perspective, from an availability of resources, and from the utility of those resources, right? And so time scale becomes very important as we consider, well, what does it look like to engage in sustainable innovation and manufacturing in Africa, as that benefits not only the continent, but the rest of the world. I've mentioned briefly the change of state, and for us, change of state has to be perpetual. As soon as we discover a new state, or as we refer to it in math, equilibrium, we are on the task to seek out the next one so that we are not caught on the back foot, right? And I think that's very important to consider in terms of the discussions that we're going to be having throughout this meeting. And then the observable duration, right? How long do we intend for this activity to stay in place, or to change? So from a system design perspective, one of the key things we look at when you're trying to define a system is, what is its useful life cycle, right? How long do I actually intend to use something in its current state before I retire it, right? In system design, we say you're not done engaging in the design process until you have a plan for its retirement, right? Or in other instances, until you graduate it to a different state of usefulness, right? And so as we have these conversations and as we talk about the grand picture, mine is to just share that the planning that comes ahead, right? The effort that goes into saying, can we acknowledge that the intention that takes place before you engage in the execution becomes as vital as the execution itself, right? And then becomes important as you maintain this activity throughout, right? So as you engage in problem solving, as you engage in innovation, it becomes so important to always go back, revisit, and say, are we still trying to tackle the same problem? So what does it mean to build systems that sustain both people and place? This is the question that I was asking myself when I was invited to come share with you guys, And in the context of Africa and the Savannah, where we're going to spend a lot of time, what does it truly mean, right? And so you'll have a session later that talks about both machine learning and AI. And as someone that enjoys technology and uses it to solve problems, I underwent the task of asking an AI to tell me what would it look like if I were envisioning, right, innovation in manufacturing in the Savannah, where we sustain both people and place. And that's the image that was generated, right? And I thought it very intriguing, right? Because as has been mentioned, right, by both Jack and Jacob, there's this idea of whenever you are in an environment, you don't contend only with the element of interest, but you're always finding yourself, especially in engineering, engaging with energy, with water, and because all of these are human activities, food becomes a core element of that, right? And so in order to be able to put up any kind of industry that will be considered useful, it almost becomes irresponsible to do that without the consideration for the sustenance of people inside this environment without destroying the environment, okay? And so I now want to share a motivator for a lot of the work that I engage in and I always go back to. A few years ago, more than a few years, over 10 years ago, I had the benefit of working on the design of a commercial communication satellite, a geostationary satellite. As an aerospace engineer, this is some of the stuff that we do. And I was exploring the differences between what we consider successful systems and systems that are not successful, right? What's the difference between what we create that we find such value in and the things that we create that are considered failures in exercise or that are considered largely not fit for the environments in which we try to adopt them, okay? And I stumbled upon works of Mike Griffin, who worked at NASA as a program manager for quite some time. And he shared a talk in which he described what he liked to call elegant systems, okay? And elegant systems, as he described them, had 4 key characteristics that we should seek out whenever we engage in trying to create something new, okay? And I always use this as a way to evaluate, have I attained a state of elegance? Am I working towards a state of elegance? Or am I veering off the path that should be sending me down that path? The first characteristic is effectiveness. The question is the thing we are creating effective? Is it doing the very thing that we intended to do once we create it? That's the first question we get to ask ourselves, right? Now, as I have done literature reviews in systems engineering and evaluated different projects and trying to institute it in my life, I have found that often as engineers, as innovators, and as scientists, we fail to properly ask this question. We are quick to jump to number 2, which is efficiency, right? We love to measure, right? And we love our numbers. Numbers are easy, numbers are beautiful, and numbers tell us the stories we like to hear. The first one is a question of how do we determine what we consider effective, right? And we engage in this process by understanding who are the beneficiaries of anything we want to create. So we call these people the stakeholders. And so one of the first things we do when we're engaging in any exercise is understanding, well, what do our stakeholders need? And who are these stakeholders, right? Whenever I teach my students in class, I'll ask this question: who is a stakeholder of a system, okay? And it takes the same flavor year after year. When I ask the question, who is a stakeholder, they will give the initial same responses. It is the owner of the company. It is the manager of the team. It is going to be the employees that are working on creating something, and it is going to be those who purchase the product, right? Those are the typical answers. And then there's silence, and I say we haven't exhausted the list. And slowly they begin to confront, well, who else could it be, right? And they'll eventually get there. We say, okay, if there's a company that's trying to create something, we don't do it in a vacuum. We live in a society, and that society, right, has an engine known as government, right? And therefore, those become stakeholders. Because we don't create engineered products in vacuums, we create them within societies that have rules with regard to how we can create, engage, and use certain things, right? And so you have this bigger conversation of whether or not they're purchasing your product by mere virtue of the fact that they exist in the environment in which you're creating it, that is a stakeholder to the thing that you're trying to create. And so have we asked the appropriate questions to these stakeholders of what they would consider to be effective? I was once in a graduate class on systems engineering, and I had a wonderful professor who gave an example of failed engineering. And this is the example he gave. He said, I once worked in Kenya. We had been deployed to start up a fish farming project in Lake Turkana. Lake Turkana is in the north part of the country. It is a freshwater lake surrounded by desert. Okay, just to provide some context for those that don't know where that is. And he said part of this was identifying that this lake is full of fish. Okay, it's absolutely full of fish to this day. And so they said, given the rest of the area surrounded by desert, we can help those from that area by converting them from being nomads who take care of cattle to fishermen who can just live off the lake. And so they raised funds, they came, and they built a dock on the lake. And then they built a huge market where fish can be brought to the dock, where it can be sold, and where the locals would then have a thriving economy. They then built 2 types of storage units for storing this fish in case there is some fluctuation in demand so that it doesn't go to waste. They built salt storage units, and then they built refrigerated units. And they said they trained locals on how to do it. After 6 months, this project was handed over, and they left. 2 years later, they had the opportunity to come back and see how the project was going. And everything was abandoned. And his conclusion to the tale was, sometimes, regardless of how good your intent, a well-built system will fail. And that is not what I got from that. So I raised my hand in the back of the class, and I said, thank you so much for using an example from my homeland. I appreciate it. And then I asked, did anyone in your team ever ask the locals whose activity is rearing cattle in an arid area why they choose to do that? And he said, no, because it's difficult. They have to walk for miles, and these people are away from their homes for weeks, sometimes months, looking for green pasture in a very arid area. And so we thought that surely cannot be, right, the path to success. And so I said, devoid of the context of the environment and the culture of the people there, I agree with you. You built a perfect system that you deployed and it failed. However, if you'd have asked them what bearing their activity has with their personal identity and their culture, you would have realized there is seldom a greater insult than to tell someone whose entire identity and way of life has been passed down from generation to generation that the thing they are doing is meaningless. And so the problem was not the system built, the problem was the lack of understanding of the environment in which they were trying to deploy a system. And so some people took away the face value lesson. Fortunately for me, understanding the context, I took away a lot more from that, right? And I often think about that as well. When we ask the question, is this effective? It is not merely just about the thing that you engineer, but it is also about the environment in which you intend for it to be used. It is about the way it interfaces with that environment, the way it utilizes resources or how it creates unwanted outcomes, and I'll talk about that in a moment. Does your system seek out efficiency, right? This is opportunity cost. How much are you spending for the gain, right? And it's as simple as that. And so, as an aerospace engineer, the aerodynamic specialist will say, how much lift does my airfoil generate for the amount of drag that it is producing? We consider lift the benefit, drag the cost, right? The structural engineer will ask the question, well, what is the yield based off of the weight of the structure? I want it to be strong and light. The propulsion engineer asks the question, how much thrust is the engine producing for the amount of fuel it gets to consume, right? And we do a very good job of measuring efficiencies when it comes to our isolated understanding. It becomes a little different when you're talking about it in the context of the environment in which it exists, right? Because now you'll have systems that can work very well from the perspective of the designer, but are very expensive for those who don't have a direct benefit. Okay? If we decide to engage in an activity in which we are pulling all the resources from a place regardless of the abundance of the resource, and the consequence is that we get to drive people from their communities, right? We get to take so much that their basic livelihood is now changed entirely without warning to them, right? Are we really extracting the value that we thought we were going to extract from the system? Third is to develop robustness. Okay? Now, engineers and scientists have very many different definitions of robustness. I am not going to purport to have a succinct definition. The functional one that we use is the ability of a system to behave in the way you intend, even when there's a change in the system's environment. That's our working definition. So if I build an aircraft that's meant to comfortably fly without having too much disturbance and is stable at 30,000 feet, what happens when I have wind gusts that are hitting 30 miles an hour, right? This is a fundamental change in the environment for which it was designed. Do it still maintain certain levels of performance, or does it so now than at any other point in aviation history, because the climate change that has been talked about is actually being observed in the amount of turbulence you experience when you fly. If any of you have flown from Europe or from North America to Kenya before, and you track the experiences and how smooth your flight has been, there has been a steady increase over the last 20 years of the amount and the velocity of turbulence that you experience in flight. Right? So that is an observable change that we see in aerospace engineering, and is actually affecting the way we're looking at designing aircraft moving forward, because we know that unless something significant changes, this is something we're going to see happen more and more, and its intensity increase. So do we create our systems so that they are comfortable when the environment decides to provide disturbance? And then lastly is, does our system minimize unintended consequence? This one is a fascinating one. It is the only point in which I disagree with the initial proposal of the characteristics. I view this less as a characteristic, but as a response of the system to everything else that has been done. For every system that I know of in existence that is created, there is an unintended consequence. The mere fact that the definition of a system is something that produces unique behavior when you bring things together means that we should always understand that there is the possibility that we get a positive or a desired unique behavior that we could not observe before, and there might be a negative unique behavior that we didn't anticipate. So do we work and do we continue to engage with the definition, with the redesign of systems, so that as we identify our unintended consequences, industrialization, right, growth of economies that translates to increased pollution, right? That's an unintended consequence. It is not by design or desire that we want to increase pollution whenever we increase our industrialization. So what are we doing to evaluate those things so we can figure out how we change it moving forward, right? Change has to be ever present for us to maintain effective systems. I think I have a few minutes left, but with that, I'm going to say thank you very much. Leave you with another generation of AI, of what it considers, right, a true sustainable integration of innovation and manufacturing in the Savannah. Thank you.
Keep that one. All right. So those are the culmination of our talks for the afternoon. So we are going to take questions. First from Benjamin, and then kind of open it up for any of the other questions, and then we're going to take questions from the online audience. So, is there any questions for Benjamin? Too clear? Any other, sorry. Any questions? Okay, we'll open it up, I guess.
I almost made it.
Almost.
Thank you so much. I want to ask a general question for you and Jack. So we are speaking about Africa. So how do you think about the raw materials in Africa? Is you are giving to other countries just for integration or it's competition? So in my thinking, I'm thinking like some sort of collaboration and some sort of integration. So we have to think this way to build up some good connection. So I want to like hear your maybe point of view. You are Jack.
Excellent. That's a great question. My perspective is entirely going to be based from a systems evaluation of it. Right? As has been pointed out by the speakers today, Africa has lots of resources. Right? We love to call them raw mineral, right, and raw materials. I just think of them as resources. Right? It is unfortunate that in as much as we have these resources, we do not engage in majority of the activity that translates them into consumer goods. Right? So majority of what is harvested is sent away, is processed, repackaged, and then we have to purchase. Right? And there's several examples of that. We can start with coffee, tea, go down in just Kenya alone, right? Coffee, tea, pyrethrum. We could go down the lane, jeans material, right? And part of that is an engineering and a science issue, but part of that is also a societal issue, right? And by that I mean the structures that are put in place by the agreements that we make that either are not beneficial to both parties, or in the cases that we acknowledge that at the time they were instituted were not beneficial to both parties, carry clauses with them that make it so that trying to disengage from that initial agreement means that you are now violating some kind of contractual obligation. And so there's penalties that are put in place, some hidden and some very overt, that make us think twice about changing the status quo. Right? But I think the opportunity that we have is, as we, the scientific community, discover more about materials availability and the way technology can result in fast change in our environment, in our ecosystems, there's opportunities to engage in new activity without having to step on, right, the toes of those that came before and may have put those in place. So that's just my evaluation from everything that does not have to do with the science, right? I think a lot more of it in the continent has to do with society and the rules that have been put in place that are preventing what we want to see.
both going to touch on goals and ideals for development of industry and processing here in Africa. And one of the demands for that being skills development. Can you talk a little bit more about kind of the challenges that you anticipate with the development of the workforce here in Africa to be able to fill the skill and skill positions with those new industries?
Excellent. That's a great question. Where I see a challenge, where others might see a challenge, I see opportunity. Okay? I don't have a polished way of saying this, so I'll start by apologizing. I'll speak from my experiences and what I observe. Okay? My family runs a farm in the western part of the country, and we are often looking for people to come and work and engage and assist with different things. Okay? And not too long ago, we had a young lady that came to us for an opportunity to engage in the farm work, and we wanted to hire her, and she was very well-spoken, she'd gone to school. And she was just coming to assist in doing a little bit of record keeping, etc. Right? And so she was invited over. This was actually a little over a month ago. I had never met this person. I just so happened to be here visiting, helping with some of it. And her visit, after she was hired, was her first day, and she was hearing what we do on the farm and some of the things she can do to assist. And I asked the question, did you go to school and how far did you get in your education? Sheer curiosity. And she says, yes, I have 2 bachelor's degrees. Okay? And so I said, okay, what are bachelor's degrees in? She says, I first went to school and got a bachelor's in information technology. And I looked for work and couldn't find it. And so a family member was so kind enough as to send me back to school to try and get a different degree so I can find work. Okay? So that's phenomenal. What's your second degree in? She says, I just graduated 2 years ago with a software engineering degree. And I have looked for work, haven't found it. And so I started a little business where I sell vegetables on the side of the road. And I wish that was an isolated incident when it came to the continent, right? You will be surprised how much we engage in training and emphasize education, but the moment they leave, we do not have an industry that is ready to support the levels and numbers of people that have this highly specialized skilled training. And so they end up, as we call it, there's a term for this in Kenya called tarmacking. Let me share with you what tarmacking is. Tarmacking is this phenomenon where when you graduate, you are going to spend a very significant amount of time walking on the tarmac next to the road. As you go from building to building, industry to industry, just to see if you can ever find a place to employ you. And so, if you ask a lot of people in Kenya and other places in Africa, is there a concern that if there's this development in industry that we have not yet seen yet, are we now going to be wanting for a labor force? The answer I'll always give is not in the foreseeable future. So that's my response to that.
Great, thank you. Sorry.
Yeah, it's just a quick, completely 100% agree, I think, with the observations Benjamin just articulated. The only addition I would have to that is what is the training geared towards? What's the uptake? And I think this is where being interrogative in our training programs, our education system, aligning that with where we see opportunities. And these have to be globally competitive opportunities, because nobody's coming to save you. And so if you don't identify where is it that you can play, that you have an edge, and how that edge then drives the kind of thinking from an education standpoint to a level that we have now system type of thinking, understanding these are skill development that are needed for the kind of offtake and opportunities that we see in the market.
Right. Thank you, Jack. Okay, any other questions from the audience here? Okay.
without a question to you, Judge, I think you presented some pretty compelling examples of what could happen here in Africa in sustainability. Do you see the investments coming also to grant those opportunities, whether from Africa itself or from other sources, that you then get actually the means to transform this into the future that you want to see?
So the short answer is nowhere near the scale of the opportunity that is available. The long answer is that we do have certain private sector that is already seizing this moment, even in the absence of an enabling environment, even in the absence of a struggle in terms of the financing that is needed. Because there's a long list of opportunities that are absolutely competitive. The moment you layer on the cost of capital, it washes away the competitiveness. So there's a number of binding constraints that we do need to address that then enable us to get to the truly transformative kind of impact that we foresee. And part of that process is starting with the recognition of the opportunity, period. Because we are at the point where that opportunity is not conventionally even recognized. And that's just a quick example of that. So one of the most compelling ideas when you start thinking about some of these opportunities has to do with the opportunity on direct air capture. And you know, there's scientists in the room, so I'm not really trying to explain what that is. But you think about what it needs, what are the ingredients that make it feasible, or at least provide you kind of the edge for direct air capture. You need a place with a kind of energy, green energy, that is, because of it's an intensive, energy-intensive process. So you need a place where it can be able to support with green energy from at a scale that obviously has not been seen in the past. And then secondly, you require a place where these green electrons that are being used to support the direct air capture process do not have other competing uses. Because I would argue, if you're generating green electrons, the first and foremost priority should be to retire emitting energy sources, not directly to direct air capture. And then of course, ultimately, we need a geological structure that allows for the storage when we do that capture. You start thinking about that, and you find a place in East Africa where the Great Rift Valley is running through with the right geology, with geothermal power, and an ability that you can be able to do this without compromising on other sort of emitting sources, because there's really no that much energy, and whatever is available is mostly green. Why is that even in question? Why we need to locate and set that up in a part of the world that aligns with those incentives? But the moment you share this as an idea, and I know this for a fact from some of the companies doing this, they have presented this as an opportunity without names of where that opportunity resides. And to a person, investors will be all on board, sign me up, tomorrow we get going. And the moment they go, oh, and this happens to be in Kenya, this happens to be in East Africa, everything falls apart. And they're like, oh, you mean this is not in the Pacific Northwest? Somewhere close by? And just because it's an unknown, it's a location where most of what they know is perhaps information that we see on CNN, and most of that is leaning more, it's biased towards everything that is not working. It's not to say that that is not true, it's just there's no balance in the kind of information that is available to them. So there is a lot of education process, a narrative shaping work that allows the kind of investment that we need to start seeing to flow can be realized.
Okay, great. For the sake of time, allow me to switch. For the sake of time, please allow me to switch to the online panel. I think we have Aris in the picture. Hi, Aris. Aris is joining us from Peking University. A little bit about introduction about Aris. Aris is, I don't even know how to describe her. She's like a power of nature. She moves stuff. Alice also know her. She's a professor at Peking. But when COVID hit, Alice and Paul White started this forum called ICONX. And what ICONX translated to forum where we can have these kind of discussions, where we can be open-ended. We can talk any subject. We're not limited to any specific area. And besides ICANX, which is doing very well in all aspects, she's also an amazing professor who does a great work on wearable and flexible electronics. So I don't even understand how she gets to balance her time. And in a little way, I think Benjamin was telling me I'm going crazy, pushing different areas. I steal those ideas from her. When I grow up, I want to be like Alice. Right? So Alice, do you have a question for us? I can hear you, but I cannot project you to the room. Yeah.
Yeah, so the question that some of our team have been working on combining diverse data sources, data streams, to understand using machine learning, which is a component of AI, to learn where phosphorus hotspots are in certain geographies. So we also have an initiative called Convergence Informatics, where we combine data from different disciplines to answer unique questions, like where are certain underground water resources or minerals and things like that. So you're going to see it pervasively, I think, throughout all of these different application spaces. But I'm not sure that there's a global approach. I think I'm thinking it's going to be specific to specific problem statements. But I'll pass this off to anyone else.
Well, I think I will look at it from, we were talking about the potential in terms of renewable energy on the continent. And when you talk about AI, there is energy-intensive computing that needs to accompany that. And we just so happen to align, the whole AI setup with data centers, AI training. That whole industry happens to tolerate the kind of, latency that sometimes you find in that grid. So it becomes actually a low-hanging fruit as an off-taker of the renewable energy that is available in this part of the world, and setting it up as sort of one of those initial opportunities that enable the investment again in terms of generation capacity. And you do that, there's nothing that stops you from starting to progress further along the value chain. Because, for those who may be familiar with Kenya, Olkaria, which is about 2 hours away from here in Naivasha, is one of the locations that most of the geothermal generation within the country resides. If you were to set up data centers within that location, within that neighborhood, and you have an adjacent town in Naivasha, what is to prevent that you make Naivasha essentially a smart city? And by so doing, you start realizing all these digital jobs, all manner of different opportunities that start to emerge, and you create an ecosystem around that that becomes somewhat of an anchor as you can bring other innovations around. And that's sort of the longer term, the more broader thinking that when you think about AI, you think about the structure that needs to accompany that and how that leverages the competitiveness of Africa's energy resources and renewable resources at that, and to enable that can be unlocked.
Thank you very much. Alice, you have another question? Or any other question that came through the platform?
questions. What you're asking, the fact that we may be data limited, we're often data limited, and that limits the applications of AI. Yeah, and I think that the real challenge there is not in AI literacy or AI application, it's in availability of data. One of the things that we're seeing in the US now is the turning off of certain government data sources. I don't know what's happening throughout the rest of the world, but I think that this further perpetuates the problem of our access to good data. So I think that should be a separate and equally important conversation.
And actually, I can jump on that. One of the things that Iris said, we are very keen at Connect, is bringing people together. Although we may be limited in data, one of the things that AI can help us is to bridge fields a little bit faster. Because the days of reading volume and volume of books and guessing which one is going to be okay, nowadays it's ChatGPT. I can go to one of those and randomly send me all the system engineering stuff. I have no clue what it's doing. But then, as you showed, we can communicate, although we're coming from very different fields. So some of the limitations in our field, if we scientists take the initiative, we can use AI to organize. We can use AI to penetrate fields that we're not very good at, but we can find the right people. Thank you. Thanks everyone. Thanks, Iris. Bye. Right. And we are offline, so now we can come back. Well, I tried many things, but I will not lie to you, that was very challenging. Trying to complete time zones and trying to make sure everybody's there, that was no fun. Any other questions?
My question is to Jacob. You say that the phosphorus fertilizer is 20% efficient. So is there any disruptive technology that can be used so that you improve the efficiency, the usage, so that we can address the human, plant, and environmental health, so that we don't repeat the same mistake? But I guess the economic impact on the phosphorus exploitation is going to be huge.
I'm glad we're offline now because I may make a comment that will come back to haunt me. But just to reiterate what you said, that traditional agriculture, the food system is only 20% efficient with respect to phosphorus. And that's defined by the fact that we have 20% entering the human body, and 80% being unaccounted for, lost to soil and surface water. So there's an important aspect to this, and I don't want to dismiss it, an important aspect to increasing phosphorus use efficiency in plants. But there's a bigger problem of that 80% being lost, right? So you asked if there's a transformative approach in order to deal with that, and I would say you have to get away from traditional agriculture because you're always going to struggle with these problems. Look at hydroponics, look at cellular agriculture. There's significant growth in cellular agriculture. It's a trend that some traditional agriculturalists don't like to look at. But in a cellular agriculture approach, you have a well-defined system. You don't lose phosphorus to the environment. You can recycle your waste streams and things like that. So it's a much more controlled space. That said, I don't think we want to see ourselves in 50 years just eating food pumped out of the factory. So I don't know what the balance is there. And I think we should have some really good conversations as a society and also with our dietitians. Thank you.
But can I ask a question on that? Actually, I want to follow up on that because when it comes to agriculture, just before I say this, how many of us are working with agriculture? So speak up. All of the people in this room, how many of us are working on any field related to agriculture? Right? Okay, so we're a number of us here. This is unusual. If I ask that question in a materials session, yeah, very few people. So how do we fund research in agriculture where it's not, for lack of a better word, sexy? It doesn't look, you write an NSF proposal or any proposal on that, it doesn't have the buzzwords that actually catches people. So how how big is it funded? How big is it going?
Martin, I think that this is regionally specific, right? I can answer with respect to the U.S., and I would say the proposals you submit to the National Science Foundation that touch agriculture are written completely differently than the proposals you submit to the USDA, for example. So you could do more traditional agricultural research through USDA grants than you might be able to do through the National Science Foundation. And that's to our benefit. That means that we have a portfolio of funding agencies that, in an ideal world where they're actually funding research, fund different aspects of research, the basic research and the applied research. You want to add to it, Owen?
DOE has their own language on this too.
The Department of Energy back in the U.S. Also touches on this space. And ARPA-E, which is a Advanced Research Projects Agency, so like a DARPA-like equivalent of the Department of Energy, and NASA. We're getting a lot of U.S. agencies up here being listed, but we don't know which ones are shutting down.
No one does.
Any other question? No?
Here, I'll go.
Is the mic?
Yeah, that's a quick one. Are you doing any work with Morocco? Are you doing any work with Morocco?
Yes.
Okay.
That's an answer. I was informed by my niece that you're not supposed to use sexy anymore. That project has Riz. So Riz is the word
Fire.
to use. That is fire. See?
It's fire. The question was, are we doing anything with Morocco? So you all noticed the bar chart in my presentation showing Morocco having a large fraction, in fact 70% of the world's phosphate reserves. They supply phosphorus to a large portion of the world. Think about Brazil. Brazil, for the most part, doesn't mine their own phosphorus. They import it, including imports from Morocco. And we believe on the U.S. side, we have a Phosphorus Sustainability Center. We source most of our phosphates domestically. We have mines in Florida, North Carolina, and some other places, but we do rely on a little bit of imports. Now, we have started collaborations with Moroccans. There's a university. So in the Moroccan space, if OCP, it's an acronym for French name, is the company that controls the phosphate mines in Morocco, and they funded a university less than 10 years ago called University Mohammed VI Polytechnic, UNCP, and it's growing very rapidly, and they're very much interested in facilitating the sustainable growth of Africa. And how that plays out, I don't know. I'm not responsible for their mission. I'm not responsible for how they interact with other African countries. And we recognize that it's highly heterogeneous here in Africa with all the different laws of the different countries at play. So we started collaborations with them. We have a memorandum of understanding. We're sending students and faculty back and forth to start collaborations. But we struggle because it's difficult to find a funding agency that will fund research across those two different divides. OCP typically funds research at UN6P. We'll get research funded by the National Science Foundation, but there we're looking at things like foundations, like the Gates Foundation, the Bezos Foundation, Novo Nordisk, things like that. And that's a difficult space to break into. But I think just to quickly try to end my response to your very important question is that there are opportunities that are unique in Africa that need to be addressed that are different from those in the U.S. and are different than those in Europe. And I don't know which agency is funding that research. And I think it's important that it gets funded somehow. Because in Africa, in particular sub-Saharan Africa, you have phosphorus deficient soils. We, for the most part, don't have that in the U.S. We have a problem with excess. In Europe, they conquered recyclability and recycling of phosphorus. And so wherever the resources come from, I think that we should try to do our best to make sure that the challenges in Africa are uniquely identified and addressed prior to that growth in population. It's a pipe dream.
Good. Thank you, Jacob.
So yeah, thank you very much for this very inspiring section. And I was kind of wondering, so far we always talk about university or research institutes and companies try to kind of translate the technology that happens at university. So what would be the role of a non-for-profit organizations in this type of advancing this translation of knowledge and also interacting with the society? the point of view of yours? Any of you could help to answer that.
I think excuse me, non-profits would be perhaps benefit from a lot of the research that is coming out of the universities. It's a way to test and prove the viability of those research opportunities, even before in a pre-competitive state, and enabling that that research is not just sitting on some shelf, and it can be tested against the realities of implementation. And I think once proven, then it creates sort of the basis for the private sector to jump in now, with the ability that there is actual evidence of this research being workable. So that bridging between the research to competitiveness, with NGOs or non-profits becoming somewhat of a bridge with the benefit of philanthropic funding.
Great.
At least that's my mind's sort of most cost-effective way to put it.
Right. Any other questions?
So in your presentation on phosphorus, you specifically mentioned Nigeria. Is there any activities going on in Nigeria now in terms of phosphorus?
I don't feel like I'm an expert enough to accurately answer your question. I can tell you anecdotally what I've seen, because we have tried to reach out to Nigerian researchers to find out more about what's happening on the grounds, to see if we can formulate a problem statement with respect to research. And we have difficulty finding researchers that work in phosphorus sustainability in Nigeria.
Okay, maybe I'll have to take it home while going on the issue of phosphorus. We have to discuss again. If I go home, I will check if there is activities going on in that area.
Yes, thank you. Thank you for helping. And I think all across Africa, in particular in the countries where significant growth is expected, not just population growth, but agricultural productivity, where we expect more fields to be used, for example. That's the driver for that 963% increase that's projected for phosphate inputs into Nigeria. So it's not just Nigeria, right? This is what I'm saying. It's all of these countries together. We have, in the fall of this year, there is the largest sustainable phosphorus meeting being hosted in Ghana. It's in late October, early November, I believe. It's called the Sustainable Phosphorus Summit, or SPS. So I would put it out there that if any of you are working in this space or know others, it would be great to leverage your connections to make sure that we do our best to reach out to African researchers to enable them to participate in that meeting.
Great talk, all of you. Thank you very much. So my question kind of goes with what he asked before is, as scientists, we all come up with these sustainable solutions and all of these innovative ideas, right? But how do you take this and translate it to the society that can be widely used very quickly and not in a very cost-effective way, but also in a way where everybody of the society can kind of adapt it? Is that just from a policy change perspective, or can we as researchers do something about that?
And actually, that's very nice because that's coming from one of my mentees. So what I would say is, I believe in one thing. There is a language everybody understands, but we always run away from it. We don't want to put it on the table. Money, right? So if you have a very good solution, make money out of it. That is my philosophy. Because you can try to preach as much as you want about how beautiful the idea is, but until you show that the idea is a solution, then you find the person who needs it, the person who has the pain, they will pay you for it. And they will not pay you to put in a shelf. They will pay you so that they can make more money. They will make a fool out of you. They will think you don't know what you're doing. And guess what? They can see $1 million out of you every 10,000 they give you. So, and I think that's a challenge, especially to those of us in environmental sciences, to think about how do I become an entrepreneur. And unfortunately, every scientist is an entrepreneur. We all know how to do HR, we all know how to do accounting, we know how to do recruiting, and we know how to do firing, right? So you already have those skills. Why just use them in your research group? and not translated into an entity that relates at the time. We are very big non-profit. Because we raise money, we do one, but we don't have a return on investment. The hope is the work we're doing one day will be translated. But some of these, especially when they're so close to you, I would encourage, especially the students with postdocs, think of that.
That we're just dumping the phosphorus out into the environment and we can't recycle it. So it kind of begs this question of, can we embed these in a polymer or something that will allow us to recover it? But then how do you have the trade-off of, okay, now this is recoverable, but is that really a scalable and sustainable solution? Like, how do you deal with, about to get too technical, like some of the mass transport limitations that happen when you start kind of moving?
Yeah, I'll try to address it on Thursday. It's actually, Jacob early put a point in how difficult it is to remove the captured phosphorus from phosphate from the target. So we actually have a really cool technology. We can release 99+% of the material with very, very mild condition on the floor. So we are going to be scaling up and seeing how far we can make it. So we don't have the scale up data, but we have a proof of principle. So just wait until Thursday. That's a great question, actually.
I'll add to it a little bit because I'm not going to talk about hydrogels on Thursday. You're going to talk about hydrogels. But I'm glad you asked the question. It's the right question, and there's not an easy answer. There's not an easy answer in hardly any area of science and technology with respect to scalability. In the area of phosphorus sorbents, it's especially challenging. The bentonite example that you cited is a very expensive material, and it's only used in situations where you really need to prevent eutrophication in harmful algal bloom. Imagine you're hosting the Olympics, or imagine you have a critical fish supply or something like this, or a critical water supply for a city. So you might invest in a solution like that, but it's very expensive. So scalability, I just visited Northwestern University last week, and there's another phosphorus researcher up there, Vinayat Drogi. He's a material scientist. Other material scientists do this too, this wacky phosphorus stuff. And he developed what he calls a pearl membrane. And pearl is an acronym that stands for something, but it's basically a sponge material that he infiltrates with iron oxide. And it works really well. And it's recoverable, and you can reuse it. He's demonstrated reuse. It's not the best sorbent ever, but it's reusable and it's cheap. And I asked him this very question, because I saw a startup company also, he's got like 4 employees in a startup company selling this stuff. I said, did you ever do like an analysis of scalability? Did you ever do a techno-economic analysis or anything like that? He's like, no, Jacob, it's so cheap. Why would I bother? It's like he's using just these very simple materials that can be sourced. And so he's just thinking intuitively, like, this is just a scalable technology. So I don't know. I mean, you could do it more rigorously at the outset of your research. Like, we're looking at a lot of different inorganic materials, and I ask my students about scalability. Like, what's the cost of zinc? What's the cost of lanthanum? What's the cost of hydroxide form? What's the cost if we deposit it on atomic layer deposition? What's the cost of, like you said, take nanoparticles and embed them in polymers? And I'm going to close my comments by pointing you back to Professor Jan Ginzer. And I think on Thursday what we need to do is challenge him on his calculations for scalability and techno-economic analysis. But I would add to what he said by saying that the more repetitively you can use the material, the better off you are with justifying scalability, right? And the cost of investment. It goes back to the Cessna 150. 150, right? Yeah, 2 seat. Use it over and over again.
Another idea that I worked with Martin on is burning things. I wonder if we can just take some of these organics that are latent in phosphorus, burn them, and then put the biochar back into them. We'll discuss. Any other questions? All right, I think we are wrapping things up. There are refreshments, I think, out in the atrium, I suppose. And then we will reconvene with the groups. And so, if your first name, I don't remember where the list is. We'll make an announcement out there. Basically, by your first name, there'll be a group in here, or 2 groups in here, and 1 group in the room right next door. Okay. Sorry. Opposite. Sorry. One group here, 2 groups over there. That will be after the refreshments. So we have about 15 minutes for everybody to grab a
I also want to say that as part of this conference, we have an opportunity to write a perspective to non-letters, right? That's a pretty decent journal for us to put our hands into. And so some of these questions that we're going to be asking, we will ask you, every group find your leader who can record the feedback. Then Johan and I, after the conference, we're going to start putting that perspective together to capture some of these ideas. We need to educate the people in Nanowal about Cessnas. I didn't know about that, and he's my friend. The other thing we also need to do is, as the conversation keep going, the reason we chose these three very broad themes for the opening ceremony is if you're already prepared your talk and you know somewhere you can insert some of these things, please do it. Let us develop kind of a common language, because we will do this again. There's already things blowing, and we might convene again in less than a year.
All right, so to finish things off, I'd like to thank our three speakers once again. Can we give them please a round of applause? And that's it for right now, so everybody grab a drink.